Good morning, champs. In the previous video, we used a simple linear velocity profile to understand how shear stress depends on the boundary layer thickness. That model helped us build intuition, but it is not very realistic. In real boundary layers, the velocity profile is curved. Near the wall, the velocity increases very rapidly, and near the edge, it smoothly approaches the freestream velocity. So in this video, we improve our model by using a polynomial velocity profile. We assume that the velocity inside the boundary layer can be written as a third-order polynomial in the normalized coordinate y over delta. So we write u divided by u infinity equals coefficient 0 plus coefficient 1 times y over delta plus coefficient 2 times y over delta squared plus coefficient 3 times y over delta cubed. Our goal is to determine these coefficients using physical boundary conditions. First, at the wall, where y equals 0, the velocity must be 0. This immediately gives coefficient 0 equals 0. Second, at the edge of the boundary layer, where y equals delta, the velocity must match the freestream velocity. This gives coefficient 1 plus coefficient 2 plus coefficient 3 equals 1. Third, at the boundary layer edge, the velocity gradient should vanish. This ensures a smooth transition to the outer flow. Taking the derivative and evaluating at y equals delta gives coefficient 1 plus 2 times coefficient 2 plus 3 times coefficient 3 equals 0. Fourth, from the boundary layer equation, the curvature at the wall is 0. This gives coefficient 2 equals 0. Now we solve the system. Since coefficient 2 is 0, the equations simplify to coefficient 1 plus coefficient 3 equals 1, and coefficient 1 plus 3 times coefficient 3 equals 0. Subtracting these equations gives 2 times coefficient 3 equals minus 1. So coefficient 3 equals minus 1/2. Substituting back, we get coefficient 1 equals 3/2. So the final velocity profile becomes u divided by u infinity equals 3/2 times y over delta minus 1/2 times y over delta cubed. This is a much better representation of the real boundary layer. The profile is steep near the wall and flattens near the edge, with 0 slope at the boundary layer thickness. Now we compute the wall shear stress. We use Newton's law of viscosity, which tells us that shear stress equals viscosity times the velocity gradient. Taking the derivative of our velocity profile with respect to y and evaluating at the wall, we obtain tau at the wall equals 3/2 times viscosity times u infinity divided by delta. Compared to the linear model, this predicts a higher shear stress. That makes sense because the real velocity profile is steeper near the wall. So even though this polynomial model is still an approximation, it captures the essential physics much better. In summary, we improved our boundary layer model by introducing a polynomial velocity profile and determining its coefficients using physical boundary conditions. In the next video, we will use this profile together with the von Karman integral method to determine how the boundary layer thickness evolves along the plate.